Kate Evans is actually from the Oak Ridge National Lab at DOE, and she's a group leader for Computational Earth Sciences group and is also part of the Climate Change Science Institute at Oak Ridge. She's got broad interest in Earth system modeling. She's part of the activities for ACME, which is the Accelerated Climate Model for Energy, and she has extensive interest in high-resolution modeling. She's got many publications on climate variability-related activities and extremes. But in addition to that, she's also the Oak Ridge site PI for a large effort. It's a computational effort that focuses on the validation and verification for predicting ice sheets and climate evolution at extreme scales. The project is called Pisces. It's predicting ice sheet and climate evolution at extreme scales. And so she will talk to us today about the work that she's doing for validating and verifying ice sheets and the software system that she's developing, that she's involved in as part of the larger team. So Kate, the floor is yours.
Thank you, Renu. That was a nice introduction. I appreciate that. And thanks to the Modeling and Glacier and Fjords teams for hosting this talk. Can you guys hear me okay?
We can, Kate. Thank you.
Good. And you can see my slides, I'll assume. So I'd also like to thank my collaborators who are listed here on the title slide. We have many collaborators. The DOE projects are large, and that allows us to get expertise from many different avenues. And thanks also to support from the Department of Energy, particularly BER and OSCR, who have actually shared funding for this project. So as Renu mentioned, I'm leading an effort to develop a verification and validation capability for ice sheet modeling. And I'd like to talk to you about that today for two reasons. One is because we just did a release, and so we're interested in having people try out and use our software. But also because we're extending it to connect to observational data sets and reanalysis data sets and things like that. And so we're looking to connect with other parts of the Arctic community, specifically doing ice sheets observational work. So I'd be very interested in any sort of conversation that we can have to sort of better connect the type of validation of models as well as you know, observational data collection, so we can both optimize our work. So with that, I'll move to the next slide. So I'm trying to move to the next slide. There it goes. Sorry about that. So first of all, as all of you are aware, melting ice. Yeah, can you see my slides?
Kate, there is a long lag here, just so you know. Now we have the second slide.
Okay, that's good to know. I'll try and be proactive in slide advancing. So melting ice sheets are a big deal for climate change because that probably will be the most impactful result on humans. Particularly, we'll see that in sea level rise. And as you see with the figure on the left, the projection of sea level rise provided by the IPCC shows significant sea level rise due to melting glaciers and continental ice sheets. There's also the impact due to the melting ice sheets providing cold water, an influx of fresh cold water, particularly in the North Atlantic. I just grabbed this picture from NOAA from an article that came out yesterday where they showed the land and ocean temperature profiles from January through September of this year. You can see, of course, you can see the El Nino, which sticks out, but also the North Atlantic cold temperatures, and this may be due to melting ice sheets. Other significant impacts include things like the change in albedo from melting ice sheets that darkens them and provides a positive feedback for increased melting. I've moved to the next slide, so hopefully you'll see it soon. The climate community recognizes this issue, obviously, of melting ice sheets, and DOE in particular has been investing in the development of ice sheet models in order to address this problem. The idea is to develop a predictive capability of ice sheets, which I'll discuss in more detail in a minute. Back in 2009, they funded ISICLES, which was a DOE ASCR consortium, which comprised 6 projects. 2 of them I'll mention here. CISM, which I led, was to develop a parallel and scalable community ice sheet model so that we could run continental scale with high resolution and for the first time really see the dynamics of ice sheets on continental scales. There's still lots of work to do there. There's also Bicycles, which is a project from Berkeley. This was to develop a new adaptively refined ice sheet model. They particularly focused on targeting the grounding line and monitoring the grounding line as ice sheets melt and change. And they focused in Antarctica, where CISM focused mostly on Greenland. And then Pisces, which was a DOE BER ASCR SIDAC project, that's scientific computing through discovery through advanced computing, to develop the next generation ice sheet combining these efforts, and also with additional focus on validation and verification, uncertainty quantification, and also coupling to Earth system models, in particular ACME, which came about a year ago. That's the Accelerated Climate Model for Energy that DOE has spun off from CESM. There have been other projects as well. Now I'm moving on to the next slide. The community ice sheet model, which is the DOE-supported model that we're now working in, is continental scale, as you see here. Here's a picture of Greenland, although we can also do configurations for Antarctica. Performance scaling is substantial now, meaning thousands of processors. It's also a function of the numerical properties of the solver, meaning we have a solver with many layers of iterations to try and give as much efficiency and accuracy as possible. So we have a preconditioner, iteration parameters, input-output, and various things that help with efficiency, but also make the solver quite a bit more complex. It can solve 4-kilometer, 2-kilometer, and 1-kilometer resolution configurations of all of Greenland. Those are evenly spaced at this time. And so we're not limited by the throughput of the model, but the configuration. In other words, getting a good initialization so that we can run it forward and have a nice modeling of Greenland. So development at this time is focused on the use of more advanced grids. So rather than have high resolution all over the Greenland, this model is tailor-made for regional refinement. So we have efforts to look at statically refined grids through the NPAS framework. That's a framework being used in the ocean and sea ice parts of ACME. So the CISM model is going to connect to that as well. And also look at adaptively refined meshes using the Berkeley Chombo method, which is structured. So as you see here, a picture of the 5-kilometer model. On the next slide, I want to outline the goals. Particularly, we'd like to have a predictive capability for ice sheets, both by themselves and within the coupled Earth system model. And those goals are as follows. We want to provide a good initialized state of ice sheet thickness and other parameters, particularly things like sliding. And that's hard because obviously we need to connect to observed data sets. We want to provide stable simulations. So once we initialize our ice sheet model, we'd like to run it for thousands of years and maintain, with even forcing, maintain that ice sheet for a long time to show stability. That requires good optimization of the parameters and the forcings. We'd also, with a stable simulation capability, we'd like to estimate model uncertainties. We'd like to play with the parameters and see how sensitive it is to changing various things like sliding, warmth, surface mass balance, and things like that. We'd like to reproduce present-day ice sheet behavior. So, of course, once we have a nice balanced ice sheet model, we'd like to actually force it with observed conditions and see if we can match observed behavior of the ice sheet. That is sort of a watershed moment of being able to reproduce and validate the model. And then we'd also like to produce simulations using future scenarios. So take the present-day capability of the ice sheet model and run it forward in time for various scenarios and see what the impacts are, and also look at the uncertainties. Moving to the next slide, the problem is that we don't have a comprehensive strategy to verify and validate these models that we're building with those goals in mind. Now, just to define verification and validation, they mean many things to many different communities. We've adopted an approach which is commonly in use in many science domains. Verification specifically meaning that we want to make sure that we've implemented the equations and other parameters as we have designed them. So in other words, we're solving the equations correctly without bugs or issues or problems in the intent in implementing our model. And validation we define as actually deciding or determining whether our model faithfully represents Earth and shows the ice sheets as we expect. So first, there's sort of making sure our model is implemented correctly and then seeing if we in fact have the right model. So those are two separate things I'll mention throughout the talk. And as you can see here, a schematic from Steve Easterbrook sort of visualizes this. You have your problem and then your specification of the problem, your implementation, and then obviously running it. So you both verify and validate as you go. As far as verification goes, we have idealized test cases already in the community. We have dome cases. Those are circular sheets of ice that move. We have shelves of ice, streams, various sort of very idealized simple problems so we can see how well the ice sheet is properly moving given the equations that we have. We also have manufactured solutions where we take our equations and we actually prescribe an output. So if we say we want it to move with a certain speed or type, we then back out to see what the initial conditions should be and then implement that in our model to see if it's done correctly. It's sort of a verification when you don't have analytical solutions. There are also some standalone and partially coupled model intercomparison protocols, or MIPS. We use MIPS throughout the Earth system and in the IPCC. There's the ISMIT, which is the European Ice Sheet Model Intercomparison. I probably won't get all the acronyms perfect, but hopefully you'll get the general idea. You can Google any of these to find out more information. There's ISMIP-HOM. That's the ice sheet MIP for the higher order model. That's a better approximation of the Stokes flow that we use for ice sheets beyond just a shallow ice approximation. There's also the marine ice sheets MIP and various forms of that, like the 3D MIPs and things like that. Moving to the next slide. So we have now decided and released the first version of the Land Ice Verification and Validation Toolkit, which I'll call LIV for the remainder of the talk. The LIV toolkit is designed to sort of codify and take together the best that we have in the community for verification and validation and actually allow the community to use it to evaluate their ice sheet models. And we hope this will be community informed and based. We released it so that others can take the code, and it has a license which allows others to upgrade it. And I'll give more details about how one could apply and update it. The idea being that as the community develops these ice sheet models, we want to have something to track as we go, but also as we get new observations and test cases, be able to add those and make it better over time. So we'll do verification with all these benchmark problems I mentioned. We'll validate the simulations against observations, doing a robust comparison to regional models where we have them. We also want to do performance verification and validation. So in other words, we're not just tracking how well the model solves the problem, but how well the model is performing. This has been a problem in Earth system models. We often have performance bugs get in the model because it's not being monitored. There are ways to make the model more efficient, or we've done things to limit the efficiency that we don't notice. So we're now tracking performance issues that show up in the model. And also we can figure out how well our model does when we add a new feature. In other words, if we add an expensive new feature, how much is that going to slow down our model? We want to know that before we include it. We also want to provide an infrastructure for validation of climate forcing simulations, both in the coupled mode and also just for ice sheet models. So we want to provide that infrastructure, and that is actually a lot harder than it sounds, mostly because of the lack of data and stuff to start with. So in any case, moving on to the next slide. So this LIV toolkit, the attributes are, it's Python-based. Python is a common language now used for post-processing of model data. So a lot of domain scientists know how to use Python. One benefit of Python, and I can say this as a domain scientist myself to some degree, is that Python is easy to use at a basic level, and you can learn more about it and use more complicated features, but it's pretty easy to get in there and play with. It has easy readability and adaptation, and it has links to other software and languages. So we tie to plotting software such as NCL, which a lot of us have used, Jinja, which is how the web software that we use, that's how we actually visualize all our results on a website, and R, which is a statistical package, so we can do some statistical analysis of the model runs. It's extensible, so we can add new features and tests. We've designed it so you can add a new test yourself without having to know the whole bits and parts of the code. And so as we get new users, we hope to improve that over time. We also target both running on desktops for small simulations and leadership class computing. So Department of Energy is invested in large-scale computing, and so we can run these very high-resolution models. And that's where I've sort of been an area where I've been working. And so we want to test these models in the largest configurations to see how well they can actually perform at high resolution, both in terms of performance and quality of model run. So the release itself has certain initial features. We've established a basic verification capability. The validation is what we're developing now. So as far as what the release has, we've designed it so that users can verify and install. So when you download the CISM model, it has something called BATS, the build and test system, so that you can verify that your install was done correctly and produces all the same results. So then you have a starting point for new development of your model. You can change parameters and features and then see what the impact is on your model, and you can track that. Again, designed to be user-friendly, at least that's our intent. We tried to add as much documentation. We have a wiki. As you see to the right underneath an example website, that's the cover that we have of our website showing that we ran it, and everything is bit for bit. Underneath that, we show that we have the source code on GitHub. You can go get it. We have a wiki and also an example, so you can look and see what the website's supposed to look like, so you can go check that out later. We also perform nightly regression tests of the CISM model, and so someone else using a different model could, in theory, set that up. I'd be interested to have someone try that, by the way. It's also modular, as I mentioned. It generates a website, and we also have internal dependency management. That's nice, so then when you download your model, say, for example, you don't have Jinja, which is our web software, it will check to see if you have that software on your computer, and if you don't, it will go get it for you and build it. And so that's nice. It sort of keeps the workflow humming. Moving to the next slide. So the first thing this system does is it does model verification. So as you see on the right, I did a snapshot of the sort of front page of the verification summary. Once live has run, it outputs the whole suite of tests. As you can see, it has shelf, dome, stream, and the ISMIP test cases from the ISheet MIP. And it produces, I gave you this example because some of these tests were bit for bit, meaning the confined and circular shelf and the ISMIPs all produce the same answer, but as you can see in red, the dome case and stream case produce differences. So if everything was bit for bit with a previous simulation, it just says everything was exactly the same and you're done. You don't need to go deeper into the website. And there's a performance summary below, which I'll explain in a minute. But if there are differences highlighted in red, you can dive deeper. So I'll move to the next slide. So you can click on those particular cases and it will show you, for example, in the case I'm showing here, dome is run for a number of different resolutions, and you can see what the differences were. So it prints for the variables, the norm of the velocity and the thickness. It shows you the maximum error, which in this case is very small. And then it shows you the root mean square error, and it shows you a plot. So you can see actually in a picture where your differences in your model run are. So in other words, if there's an issue with the boundary conditions, you'll see that immediately in your picture. And as many of us model developers know, 90% of your problems are in the boundaries. And then there's a configuration file. As you'll see, there's a button there with a plus on it. If you click on that, it will show you the configuration file, and it will show, so if, for example, if you ran with a different parameter, it will highlight that difference for you so you can look at what was changed between your model run and then the output to see what the effect was. And then there's analysis too. It shows you at the bottom how your solver performed, whether it took a lot of iterations or a few iterations. So now moving on to the performance part, as I showed you, there was some performance summary data provided below. The philosophy of doing performance validation and verification, and we're not aware of anyone doing this before, but it became an issue in our coupled models, which is why we're doing it in the ice sheets. Performance isn't really talked about, but it is very important as we add new features to the ice sheets models. It really does slow the code down, often more than you'd expect, because if you add something that makes the code more nonlinear, you have to cut that time step, and there's many sort of things that can go on that you might want to keep track of. Especially when you run on these large-scale computing systems. A lot of the Earth system models are now being run on Titan at the OLCF here in Oak Ridge or at NERSC out in Berkeley, and they use many levels of parallelism like MPI, OpenMP, and even GPU accelerators, and so we want to track how that's going. And we put in new solvers, so numerical solvers have many parameters that may improve or hurt efficiency, and over time that can change. If you add a new part of your model, perhaps different solver settings would work best, so we want to track that too. So, and we may want to compare across architectures. How well does the model perform on one system versus another? So, performance verification, I'm moving to the next slide. In case there's still a lag, I'm just mentioning that. The performance verification in Live, what it does is it does plots for the dome ice sheet. That's a nice square, easy problem. And we run it from everywhere from a problem that has about 1,000 or 2,000 degrees of freedom to 10 million degrees of freedom. We produce strong scaling plots for each of the resolutions. Strong scaling means that as you take a problem, you add more processors to solve it, the solution time should decrease, so it monitors that. And then weak scaling, where you take a problem and you assign it to each processor a certain amount of work. In the case of weak scaling, as you add more processors, you make the problem bigger. So even though the problem is growing, the same amount of work per processor keeps happening. And so we track how well the model can still produce the result in a similar amount of time. So what we do is we run a suite of cases, because on these large computing systems, there's actually a lot of variability from one run to another, either because someone else is running near you on the machine and things of that nature. It takes a while to get them all initialized. So we wanted to mention it. So what we do is we run 10 cases and get the average and max and min of those 10 cases. So when you run a new case of your ice sheet model, it will tell you if you're within or outside that envelope. And so it tracks that for you and tells you. It does that not just for the whole model run itself, but it tracks certain parts of your model, like just the solver or just the input-output, and tells you if any one of those individual parts is outside the envelope of what you'd expect. For example, sometimes when you run on the computer, if the file system is slow, the input-output will take much longer than normal. It will tell you that, and so that can be useful. So as you can see here, this is another snapshot from Lib where it shows you the plots in sort of a thumbnail, and what you can do is click on them and it makes them larger. Here's one example, moving to the next slide, where I show an increased slide. So what you have here is a weak scaling plot, and as you'll see here, this is not a great weak scaling. This is just an example I grabbed. The dotted lines show the maximum and the minimum run time for each of the 10 cases, and then the solid line is a new run that we did. And as you can see, it's within the envelope, so it's expected behavior. But as you can see, the time increases as the problem size does, so the weak scaling there is not perfect. But it does show you that at least it's behaving as compared to the previous runs. So for the next slide, I want to talk just briefly about performance validation. Performance validation is interesting because we want to know what happens to the model as we add new features. In other words, what is the value of adding some new feature of your model? If you add a new albedo, oh, I just lost my slides. I hope you guys can still see them. There, can you still see them? I'll expect that you can unless you alert me otherwise.
Kate, we're on performance validation model value.
Oh,
we
great.
can see it.
Still see it?
Yep, we can.
Oh, strange. My computer sort of exploded and then it came back. Excellent. Anyway, model value. So if you add something new like an albedo feature, that may make your model more expensive, but it may improve your model a lot. So this is just sort of a back of the envelope calculation of model value. If your skill of your model, say, is measured by root mean square error or whatever the model scientist decides is important, if your skill has improved by 10%, but your model speed has only increased by 2%, you might consider that a very good value. Whereas if your model speed has decreased by 100%, in other words, it takes twice as long, but your model skills only improved a very small amount, you may not care to include that part of the model feature except in very certain circumstances. Often what happens in larger system models is everyone adds different features that they care about. The chemists will add more tracers, and the ice sheet modelers will add lots of individual glaciers and things like that, but only certain configurations actually need those features. So if you can calculate model value, then that provides the benefits to the community. By the way, this is something we haven't yet implemented. So this is more of a philosophy of something we'd like to add. We've added the performance verification, but the validation is something that interests us. Now moving to the next slide, we show that there's a table. This is just showing the breakdown, what the Liv software shows you. As you can see, it has different lists of model parts. So Simple Glide is the whole sort of main engine of the model, but as you go down, you can see individual parts of the solver. Don't worry about what those individual parts are. Things like the preconditioner, parts of the preconditioner, the I/O. The parts in blue mean that they were faster than average. In other words, the whole model overall ran a little bit faster than average. So you can go down and see why that was. So you can say, okay, well, as I go down, I see that it was in the velocity driver, and it turns out it was the I/O. In that case, that was a little bit faster than normal, not much. This is just a very simple example. But that's how you can sort of visualize what's happening with your model performance. So with that, you can see sort of what is the value to my simulation when I track it. Okay, now moving on to validation. So as I mentioned, the release of Liv 1.0 had all this verification. So now I'm going to talk about validation, which is something we're doing now. This is a work in progress and something I hope to get community input from. So this is sort of what we're planning to do, and we've implemented just a couple things, which I'll show you. So the present day simulations of the Greenland ice sheet, we consider that the classic model intercomparison in other parts. So I cut my teeth as an atmospheric scientist. So for us, running the AMIP, which is the atmosphere MIP, through the present day and then comparing your model to it is sort of the ultimate validation because that's where we have actual data. So the same thing would be true for ice sheets. The problem is that's a little tougher because we don't have data for that long, and ice sheets operate on much longer timescales, so it's harder to track changes. So our goals at this time are to take gridded data sets from the best observational realized data sets that we have, and as everyone on the call knows, that's much more limited in ice sheets. What we'd like is a simulation that covers the same time period as the data that we have, and also run a simulation as part of a long-coupled Earth system model run using observed emissions data. In other words, if we're able to take an ice sheet model and run it by itself and then also within a coupled model and faithfully represent what we can see observationally, then that goes a long way towards building predictive skill and making us confident in those model results. this plot I'm showing here from the GRACE data shows the monthly mass anomalies in gigatons from a recent Arctic report card. So what we'd like to do is have our ice sheet model also calculate these monthly mass anomalies and see how well we can do. So the validation questions we want to ask are, is a good ice sheet model, in other words, one that demonstrates good skill? These models are relatively new. As you saw, we just started doing this about 5 years ago at this large scale. So little or no validation has been done with them, with just some very general sort of initialization and running out the model for 100 years. I'll show a video at the end that just shows we're able to basically keep the ice sheet going and not melting away or growing hugely, but we need to do better than that. Also, we want to look at the observational time series. Those are relatively new, as I mentioned, up to maybe at the most 20 years. And the time scale for ice sheets is 100 to 10,000 years. So 20 years of data is not much to compare to. So we need to work on figuring out better ways to grab earlier observational data or as much present-day data as we can. And also grab community-approved standard test cases. So as a community, we want to grab the sort of community-decided upon best configuration. So everyone is using the same configuration so we can best compare it and figure out how well we're doing. So the goals I mentioned at the beginning of the talk, we're going to revisit those. The first two bullets I've highlighted in blue. So the important two things for validation are providing a good initialized state of ice sheet thickness and elevation, et cetera, and also the stable simulations. So that's something that's going on mostly by folks at Los Alamos. This is Steve Price and Matt Hoffman, who are our collaborators. Some of that requires some optimization. That's going on now. And so we hope to incorporate initialized data set ice sheet model configurations into our initial validation to try it out. And let me move on to the next slide. So one example of a problem that we have in doing that, though, for example, we do have thickness data going back for a while. This is self-consistent data. There's a typo there. That's from 1993 to 2013. So 20 years of thickness data, which is really great. And on the right, I've compared it to a recent run by Miriam Weiss-Cano. She published this in 2013. This is using a simpler form of the current ice sheet model. This is a shallow isoproximate model. So we could do a comparison here. The problem is in our new models, we need the thickness to actually initialize our ice sheet. So we can't also use it for validation except to say that we are able to maintain it. So we need to look for other data sets in order to do a proper validation. So moving to the next slide, talking about initialization, the RACMO model, regional model, has done a good job of creating a surface mass balance, which is that balance between sort of accumulation and depletion of ice over the period of interest. So RACMO is able to provide a good surface mass balance, and that's a good initial condition for us to use in a standalone ice sheet model. By the same token, we hope that our coupled model can provide that as well. It's also able to represent dynamic thinning over the same time period. So we can use the changing surface mass balance to force our ice sheet model. So that's important. The other thing in the bottom plot, this is from Enderlin, and the above one was from Edema et al. The plot below shows that, luckily, I guess you could call this good news, is that most of the melting of the ice sheets is happening from a small number of glaciers. And I know I'm speaking to the glaciers and forest community. You guys know this much better than me. But if we take these data sets as a quote-unquote truth, in other words, if we know that most of them are producing most of the melting, then we know if we are able to reproduce that in our ice sheet model, then we've done a good job initializing our model. So if we run out our model and see melt characteristics similar to the biggest glaciers, then we're probably doing okay. We don't have to measure it for, many hundreds of glaciers. So we could use that to guide our forcing and initialization, and then also our validation. So now going back to the goals I mentioned, we want to now reproduce. So say we've got a good initialization and forcing, which those guys are definitely working hard to do. We want to be able to reproduce the present-day ice sheet behavior under climate change forcing over the past several decades. So we want to be able to actually take what I said at the beginning, which was to monitor the ice sheet behavior over that time and see if we can actually track some of this increased melting that they've already seen observationally. Moving to the next slide, the validation data that we have, there's ISAT-1 and some of the GRACE data, which I mentioned, which provides some data for us. And there's future missions, which we're highly dependent on for getting more data. ISAT-2, the follow-on GRACE and things. These can be used for ice sheet validation, but the problem also is getting these data sets in a form that we can use them. So models, of course, produce nice gridded data sets in the form of that we like to see them, but of course observations go where they can go and where we think there's important information going on. So getting that observational data in a form where the models can use it and getting the model data in a form where the observationalists can use it is a work in progress. We are working together with NASA to start doing this, but this post-processing of data, in other words, taking both model and observed data sets together so that we can compare them properly, is a research project in of itself. And that's not something that's really within the scope of what we're doing, but we'd like to. That's actually the key for getting good comparisons going. And a lot of that's actually numerical work and model development work. So that's an interesting problem, but a big one. So moving to the next slide, the Live 2.0, we'll call it, which has the validation, is we'll take the model validation of Greenland. First, we'll extend our Live software. We'll take the sort of attributes I already argued that we have, which is the user-friendliness and automation extensibility, which we've tried really hard to provide. Take the model configuration from these optimal initial states and the forcing that we've done and sensitivity studies, and then take this comparison process I just mentioned where we post-process the data and collect that into repositories. So like we have in the other parts of the Earth system model, we have a collection of observed data in a form that's useful to the community. Then we can take our model data and our observational data and really do a good comparison. So this is the challenge that we've put upon ourselves, but we need many more than just us to work on this, is to take all these parts together so that we can create a robust validation of not just Greenland, of course, that's where we're starting because we have more data there, but eventually Antarctica as well. And I point you on the next slide to ISMIP 6. This is the next stage of ice sheet model intercomparison for CMIP 6. There's a website I've put up here. We plan to coordinate with their efforts. So in other words, we hope to help them with their model intercomparison, and we also hope they'll help us in informing how we want to develop our software to be the most useful for them. The goal being, of course, again, that we need to deliver projections of the ice sheet contribution to sea level rise. A key output of that being an ensemble of historical and future estimates of ice sheet contributions to sea level. That's a big challenge ahead of us in a very short amount of time when you think of what's to be done. But it's important, so that's why we're focused on that. Next slide. So another part of the Live 2.0 is the coupled model validation. What I'd like to explain to you is that it's very important. One second, I'm going to grab a glass of water. We're also interested in coupled model validation. It is very true, and I'll say this as an atmospheric scientist, that the atmosphere models don't always do a great job capturing Arctic temperatures and moisture and things like that. If you hook up a continental ice sheet to it and you don't have a good atmosphere or land representation, then your ice sheet will not be able to maintain a proper level of ice, or it'll melt too fast or too slow. So we need to monitor what's happening in our coupled ice sheets, not just in a general sense, but specifically for the ice sheet community. So while the ice sheet community is developing good initial states for us, and while the observational community is developing more observational data, we're starting our validation by looking at the models for atmosphere and land and seeing how well they're doing in that region, particularly things like radiation coming from the sun, surface atmosphere and land model variables like temperature and moisture, as I mentioned, and the surface mass balance. So we want to track that. We'd like the software, when you run a coupled model, whether or not you have an ice sheet, we want the atmosphere and land and ocean modelers to be aware of how well their model is doing in that region because it's so important for the ice sheet model community. So we want to take relevant observational and reanalysis data sets and compare them to these models and into a codified way in the software so that you can track that. So here's one example of what we're doing in Live. So we generated these and they're going into our software now. This is just one example of near surface atmosphere temperature as simulated by the CESM. This was before an ACME, but pre-ACME. So this is a CSM run from several years ago by Miriam Weiss-Kano I mentioned. So we took that data and then reproduced some of the work she had done, things of importance. So this is near surface temperature both in the winter and summer months. So if we track that over time and compare to observed data, we can actually then monitor how well we're doing. So we also want to monitor things like cloud coverage, which has been a problem in these models, temperature, and et cetera. Here's another example. These are early results. This is different forms of radiation. We have the atmosphere incident solar radiation, so incoming, absorbed solar radiation, and then albedo. These are just example plots intended to show you of the kinds of things we want to monitor. And then in the next slide, so we also looked at things like the ice sheet fraction, fraction of grid cell covered by glaciers and ice caps, total glacier fraction, things like that. There's a whole suite of things that Miriam had done, and so we're going to capture those as well, and then add some new additional things we think are important, near surface moisture and things like that. Okay, so next slide. The key to success for this software, we think, is community input and feedback. So I've explained to you that we've done this verification so far, and that's pretty much available and ready for use. Of course, we'll always add new cases as they become available. And then now the big job is validation. But the model developers, if they can just work on designing optimal present-day force model configurations, then we'll track it as it goes. This observational data collection, we are interested in forming this repository of data that's ready for comparison. And of course, we're interested in doing reanalysis. That's not something we've really done with ice sheet data, but it would be very important to have sort of a reanalysis process if we had enough data to actually collect into gridded formats. So that's a challenge for the community. Regional and glacier scale modeling community could help us provide model benchmarks, bias reduction. Regional models often do a better job over the glacier regions than the continental one, and so we'd like to monitor and compare to regional models. And also the community design of useful metrics. So it's one thing to show plots and look at pretty pictures, but of course what we want to do is create new quantitative metrics to best tell us how well these models are doing. There's a number of statistical things that are done in other communities that we'd be interested in grabbing and working with. And some of these software packages like R that we've now linked in, we'd like to take advantage of that. And so as a thank you for this is my final slide. I'd like to show you guys a movie. If you can see it, that's great. I'm thinking with the delay you can't. If not, you can go grab it from the website later. But this is just showing an ice sheet. This is a 100-year run we did of a 5-kilometer Greenland ice sheet. First, it just shows it's static, and then it zooms in to show you this is the velocity norm. So you can see the edges, particularly we focus in on Jakobshavn Glacier here. So you can see where the highest velocities are. This is just a simple 100-year simulation. As you can see, it wavers slightly at the edge. That's just showing the initial years as it goes to spin up and basically runs to a steady state. So we made this a while ago, but I just wanted to show you this is the kind of thing that we're interested in doing at first. Now we want to initialize it and make it really faithfully represent the present day. So I know I ran through that quickly. I wanted to leave a little bit of time for questions. So I thank you very much for the opportunity to share what we're doing, and I welcome your input. Thank you.
Kate, this is Sarah. We could see the video. Yeah, so thank you for that, and it is on the website. Renu, do you want to call for questions?
Yes. Thanks, Kate, for this wonderful presentation. I was wondering whether others had questions to ask. I mean, anyone on the phone?
This is Wilbert. It's a very nice presentation, Kate. I really enjoyed it. Can you explain a bit more how you do the initialization of the model?
Thank you, Wilbert. First of all, I recommend you go down the hall and ask your collaborators nearby for the details. That's not the part I'm involved with. However, I can tell you at least that they're taking the data from the thickness data sets from the NSIDC and some of these other values, the ISAT data, to actually compile together to create the best sort of complete initial state of the ice sheet. So where they have missing data, we've been doing some sort of best estimates. And then what they do is they run out the ice sheet for a while and see if it's stable. What they do first is they assume a certain amount of forcing and see if that forcing best captures the melting that we actually see. And if not, then they adjust it accordingly and iterate. So it's sort of a slow, sort of traditional process. And they're working with the uncertainty quantification folks to sort of do higher order mathematical methods to do sort of inverse modeling so they can sort of back out the best forcing necessary to give them a good initial ice sheet that behaves properly. Does that answer your question?
It does, but I'm wondering, I mean, because you have this background in the implementation of the implicit time stepping, would you also be able to do like a steady state solver procedure to it?
That's a great question. Yes, in theory, but in practice, actually, it's just such a big model. It's actually been now in one of the ice sheets that the statically refined grid I mentioned that we're working on this project called Albany. This is a Sandia-led part of the project. They are developing this sort of adjoint methods capability to help look at the sensitivities and also allow them to do sort of inverse type modeling. I don't know how much of that they're doing with that particular model, but I know they're interested in that because you're right, that would be a much faster way to develop optimal initial conditions that would properly represent, you know, the forcing that's going on, rather than, in other words, setting all the parameters, running it forward, then adjusting it, running it forward again, and that sort of thing.
Thank you.
Yeah, thanks.
This is Patrick. I could jump in here. There's two publications by Mauro Perego et al. That explain exactly, so that go into a bit of detail of explaining on using, in fact, an adjoint of one of the variants of that model to basically create, it's an initial state, it's a steady state problem, but they're basically using ice thickness data and ice velocity data to come up with the geometry of the Greenland ice sheet and with an ice flow that is basically present day, and to use that as an initial condition. And they're basically developing an adjoint of one of the variants of those dicores to do that.
Yeah, thanks, Patrick, for mentioning Mauro's name particularly. He's at Sandia. He's one of the ones sort of that's very key in that project. You're exactly right.
So, Kate, this is Renu here. I had a general question about, you know, the package. LIB seems to be a comprehensive package, but is there a way one can download, I mean, are you making it in a way such that, so that one can just download the parts needed to verify the output or to evaluate the output? For instance, you know, if you're looking at the output of CMIP 6, we don't need it to go into the, I mean, the way I think you have the package right now, it's meant for the modeling centers to use it while developing, and you know, you can use it in this iterative way. But is there a way that a common scientist who's just doing a model evaluation can use this package? I mean, are you creating it in a modular way so that it can be used by different communities of science users?
Right. So yes, the software package itself isn't that large. Actually, the big thing to download will be the data for comparison and things like that. But what you would do, the way we've designed it is that you download the software, which isn't that big actually, but then right when you run it, you actually have a flag. So you can have a flag where you say, I just want to install the model that I have already and just test that it's okay, or I just want to verify my, so in other words, we have several different customers. We have those who just want to use the model, so they would just use LIB to verify that the model they installed is correct and matches what they grabbed from the internet. Then the second customer would be a model developer. They would just say, I just want to verify the model run that I did. In other words, say I added just a feature for the performance, I just want to make sure I didn't do anything that changes the answers. Then our other customer is the one who actually is making changes to the model that actually might change, you know, the climate of the ice sheets. And so then they would use a different flag to just do the validation where they'd actually look at the science output. So yes, we do consider those different. And so you'd only activate that part of the package that you're interested in. In theory, it'd be nice to run all three if you're doing a very big simulation. But generally what you'll do is run the verification while you're doing the model development. And then while you look at the climate, you'd run the validation side.
And you can also just use it, an end user, for instance, if someone's part of the IPCC evaluation procedure, you can use this, your package potentially to evaluate how the models compare with each other too. I mean, is that a capability that you plan to incorporate?
Yeah, it would be not at first. First, just getting a validation capability for a single model is our goal. But, you know, this project's done in a couple of years, and so we'll have a validation capability for a single model run by then. But you're right, an error comparison among models and then having some metrics evaluate where they're doing well or not would be an interesting extension. And I don't think it'd be that hard to do. Once you have one model compared, adding additional ones wouldn't be that complicated from a software perspective.
Okay. Any other questions?
Yes, it's Martin Jeffries at ORNL. Kate, thank you for your talk. My question is, what sort of observations and measurements and process understanding does the modeling community need or want from the observers and measurers? What are the sort of priority areas that you see as being where more progress can be made on improving simulation of the ice sheets?
Yeah, that's a great question. I definitely think, you know, coming from the atmosphere community, we really needed global gridded coverage, but in the ice sheets, there's much more hot areas, areas that we really need to get right in the ice sheet to be able to do a good job of representing the melting going on. So first thing we did was develop the model to sort of be regionally refined so that we can track those areas with a little bit more fidelity. But from an observational perspective, which is what you're asking about, yes, if we have observed data in certain areas where the melt is the fastest, like Jakobshavn and some of these other glaciers, we want to do a good job of actually doing good comparisons from a regional perspective. In other words, I don't think just creating gridded data sets all over the ice sheet and having a gridded model in comparison is the ideal way to go. I think having I think I showed it on an earlier plot where it showed the % of glaciers in the contribution to melting. Since we know from those earlier studies that a couple of glaciers are responsible for most of the melting, we'd want to focus our observational data collection and comparison in those areas particularly. So it's a more challenging problem in a sense than other parts of the Earth system in that we need to focus on certain areas, but that does at least allow us to just grab data from those regions where actually there is more data because they know it's important, and figure out how to best incorporate it so that we can represent in those areas you know, the best comparisons. In other words, we may not need to take the metric of root mean square error of a model versus observations over the whole ice sheet, but just over, say, the top 10 glaciers of melt regions and see how well we're doing there, rather than tracking the whole thing. Does that make sense?
Yes, I understand completely. Thank you.
Yeah.
Any more questions? If not, let's thank our speaker. Kate, thank you very much for taking the time to do this presentation. It was quite useful. And we will